Hello everyone. So in this video I want to share with you a very rarely known theorem related to an ellipse. This property or theorem might appear counterintuitive a bit when we see it at a first time. Why I'm saying it's a counterintuitive? Because when I experimented this thing in my class, most of the students got failed to draw the exact diagram which matches the statement of the theorem. So I actually delayed the disclosure of the statement of the theorem so that they can struggle and they come up with some conclusive point where they get the hope to construct a theorem by their own. And in JEE coaching culture, there is very rare opportunity we get to include such kind of creativity and novel ideas in teaching style. But whenever it comes to me, I never fail to apply so. And why this idea struck to my mind that morning? Because that morning before my class I was reading, basically I was revisiting a book called A Mathematician's Lament. This is a very old book actually. It was written I think in 2007 or 2008, but I read it in 2019. But again I was revisiting and just going through all the highlights. So I actually stumbled upon one very beautiful quote, because it's already known to me, but again I revisited and I thought on it. And he says in this book is, when we say to the students that the area of a triangle is half into base into height, we are giving the answer and we are asking the question at the same time. I'm just rephrasing, I'm paraphrasing it. It's not the exact way it is written there. So that's the thing. So when the same morning I had to teach this topic, I was thinking why not I can construct it in an activity or approach to the theorem in such a way that the students will enjoy to discover the theorem by their own. In this process, what happens is the student own the theorem. They don't have to mug up and they don't have to actually forget also if they are struggling with the theorem and all. Alright, so if you want to see why I'm saying it's a counterintuitive, let's explore it. And to explore, just follow these steps and see whether you are getting the exact diagram of which matches the statement or not. So in this video, the purpose of the video is to just see that why it is counterintuitive, and again I will prove it what the theorem is, and after that we will go to the GeoGebra to see geometrically how it is possible. So if you're interested, you can grab the pen and paper and follow the steps and try to draw the diagram. So the first step is to draw an ellipse whose major axis is the x-axis and minor axis is the y-axis. So of course we have to draw an ellipse whose equation may be like that: x squared by a squared plus y squared by b squared is equal to 1, where a is greater than b. Then only the major axis will be the x-axis and the minor axis will be the y-axis. Next is draw the auxiliary circle of the ellipse around it. If you don't know the auxiliary circle is a circle which is drawn on the major axis of the ellipse. So when I take the auxiliary circle like this is a circle it is asking. So basically the circle which takes the ends of the major axis of the ellipse as its diametrically opposite points. Now take any point on the ellipse, any point, anywhere the point you are taking on the ellipse. So let me change the color. So suppose I'm taking the point here and join this point to the nearest foci of the ellipse, let us say I am joining it with this F here, and this is the join, that is segment PF, and draw a new circle on this PF. Means again you take this P and F as the diametrically opposite points of the circle and draw a circle on it. Means PF is the diameter. Now the question was, actually, when we come up with the picture, how do we know that circle we drew on the focal distance? By the way, this PF is called the focal distance of the point of the ellipse. So when we draw a circle on the focal distance, how do we know that circle is actually touching the auxiliary circle, or it is inside the auxiliary circle, or it is outside the auxiliary circle? So most of the students drew like it is inside the auxiliary circle, but some students also drew that it's overflow the auxiliary circle. Alright, so the conclusion what the students came up with, why not we can prove it, because there are only three situations can happen. That this circle what we drew on the focal distance as a diameter, it can touch the auxiliary circle from inside, or it can stay off from inside, or it can just overlap or intersect the auxiliary circle at 2 points. So this came actually as a question of intersection of two circles. It's not as a question of an ellipse anymore. Now we have to check whether the two circles are intersecting or touching from inside, or it is not touching from inside, because there is no other case that they can not touch from outside or touch from outside. So there are only three cases. So this was the conclusion point, and now they come up with like statement like C. If they touch, we can make a theorem that if you draw a circle on the focal distance of any ellipse, it touches the auxiliary circle from inside. If they don't touch, again a theorem that they don't touch, and so on. So we assume that it touches. So to prove that these two circles are touching from inside, we have to prove something about the circle. So for that, let's assume that the ellipse equation is x squared by a squared plus y squared by b squared is equal to 1, where a is greater than b, we already know. Now I have to draw the auxiliary circle. So of course the auxiliary circle has the equation what, x squared plus y squared is equal to a squared, because the major axis ends are negative a comma 0 and a comma 0. Now this is the focus I have of the circle, because this is the point on the ellipse P and this is F. So we are taking this PF as the diameter of the green circle. The green circle we call it the focal distance circle. Now this is the ellipse. This is the equation number 1, we can say. And focus of the circle, focus of the ellipse, by the way, I'm assuming at c comma 0, where c is, you can also take ae comma 0, where e is the eccentricity of the ellipse, but let's see, that's a c comma 0 only, and c is the distance of the focus from the center of the ellipse. So it's a OF is the c here. By the way, you know also one thing, that the relation between a, b and c, and what is that relation? That c squared is equal to a squared minus b squared. So these are things we know actually. Now I have to construct a new circle over here. So what we do? We have to find the center of this. And we know this f is c comma 0. We are taking any point on this ellipse, so we can assume any point in its parametric form as a cos theta comma b sin theta. So this thing we know. Now in order to prove that the two circles are intersecting each other from inside, what we could do? We should draw a line passing through the center of the bigger circle. It will also cross through the center of the smaller circle. And what we are actually intended to do, that let's say this is the point M here with the midpoint of P and F with the center of the, which is the center of the green circle. So we can say that the OM is the distance between the centers. So distance between the centers, and we are aiming to prove this distance OM as the difference of the radii of these circles. Why so? Because this, let's say this is touching this point as A, so can we not see that the OA is the radius of the bigger circle, that the auxiliary circle, and let us say the R is the, there is the MA is the radius of the green circle, that the smaller circle. So I have to prove that the OM must be equal to the A minus R, the difference of A and R. A is the radius of the auxiliary circle, the bigger circle, and R is the radius of the smaller circle, that is the circle drawn on the focal distance. So let's find out first OM. So how do we find OM? Because we know that the coordinates of P and F are A cos theta, B sin theta for the P, and F has this coordinate C comma 0. So what we do to find M, we can use the midpoint formula. So what we get, the coordinates of M as A cosine theta plus C divided by 2, and B sin theta plus 0 divided by 2, that is B sin theta by 2. This we got as the coordinates of M. So to find the OM, we use the distance formula OM. So 2-point distance formula is not so difficult here because the O is at the origin, so it makes our life easier. We can simply square these components only. So A cos theta plus C by 2 the whole squared plus B sin theta by 2 the whole squared. So what we can see here, we have to simplify it. So we can see the denominator of each of these terms inside the square root is 4. So I can take it out from the square root sign, so it will become 1 by 2 actually. And now I'm expanding also at the same time, so it will give you A square cos square theta plus C square and plus 2AC cosine theta for the first expansion, and here I have B square sine square theta. Now you can see that most of the terms are containing cos theta. So why not we can transform the sine square theta, what we see at the end here, in the cos theta as well. So let's see it, what will happen. So A square cos square theta I'm writing at the same, and then C square, and here the 2AC cosine theta, and this I'm writing as B squared times 1 minus cosine square theta. Now you observe what is going to happen. This A square cosine square theta, and from here we get B square cosine square theta with a negative sign. So it means we can take cos square theta as a common, so we get A square minus B square, which will give you C square. So I'm writing directly here C square cosine square theta. And also notice we have also one B square here, and already I have a C square here. So this C square and B square combinedly I can write as A square. So we got this expression at the end, that is C square cos square theta plus A square plus 2AC cosine theta. And this is nothing but, if you observe carefully, this is C cos theta plus A the whole squared, and we take the root, then we get out of this root, and this C cos theta C cos theta plus A mod. So this is the distance OM we got. Now if we get the same value when we take the difference of A and R, we are through. We proved it actually. So how do we get that same distance? Let's calculate it for. So that is A minus R is just A, and what is R by the way? So let me first calculate R. So for that I have to find out the radius. of this circle. So how do we find the radius? We know the P, we know the F. So we find the distance PF, and that distance will give you the diameter, and we take the half of it, we get the radius. So R is nothing but, so I'm finding this R here. So R is just half of PF. So what is PF? The distance between the point P and the point F. So P is A cos theta, and F had the x coordinate C, so A cos theta minus C the whole square, and B sin theta is the y coordinate of the P, and F had the y coordinate 0. So we are calculating again this thing. So this will give you can notice it's a similar kind of calculation we have. So it is A squared cosine square theta plus C squared minus 2AC cosine theta, and here we get only B squared sine square theta. Don't you notice that it's the similar calculation? The only difference is there we are getting minus 2AC cosine theta. So can we just replicate it? Yes. So that is going to give you that C square cosine square theta minus 2AC cosine theta plus A square. And this I can write either C cos theta minus A the whole square, or A minus C cos theta the whole square. But you notice A is always bigger than C, and also C cos theta. So this square root should be positive, so I have to write A minus C cosine theta. And this thing I'm going to place, by the way, I left this half here, so this will be half. And now I'm going to substitute this value of R at the place of R in this expression. So that is half times A minus cosine theta, and when we simplify it, we get half A plus C, I'm missing here, C cosine theta, and we got the same thing. It means now the theorem the students can construct, and it's their own theorem, that if we draw a circle on the focal distance as a diameter of any ellipse, that circle will touch the auxiliary circle of the ellipse from inside. So now, after knowing this theorem, when we are drawing the diagram, we always intentionally draw the focal distance circle, which will touch the auxiliary circle from inside. All right. So why actually at the first place students could not draw this? Because we don't know the theorem. And also if you see this figure, when we draw this ellipse, we are trained not like so meticulously to draw what we say. We are not trained so that we can draw meticulously any diagram on the scale. So when we draw the focus, we don't draw the focus exactly on the same scale, or it's in the same proportion compared to this position of the major axis ends or the minor axis ends. So we simply take the focal randomly on between this center of the ellipse and the major axis, one of the end of the major axis. So that's why. But you see that in exact figure I have F here. And where I drew the exact figure, I drew it in the GeoGebra. All right. By the way, there is another way to prove this whole thing, and I'm not going to prove it. I'm just giving the hint for it. So what is the hint? Is if the two circles are intersecting, we can also observe that the common tangent is the tangent which is touching both of the circles from outside. And if I know the equation of the bigger circle, that is x square plus y square is equal to a square, I can also find the equation of the green circle, that is the focal distance circle. Why? Because this point P I know as a cosine theta, comma b sine theta, and this point F I know as c comma 0. And we know that when we have the diametrically opposite points given, we can safely safely means easily find the equation of the circle. What is that? X minus a cosine theta, x minus c plus y minus b sine theta, and y minus 0, that is y. So this is the equation of auxiliary circle. This is the equation of circle we drew on the focal distance. Now when we take the difference of these two, let's say 2 minus 1, we get an equation of the line. That line, because you see that y, it will come in this form, I don't know, ax plus by plus c, let us say. It comes in this form. But what is this line? And why it comes a line? Because if you expand this, of course, x square you get here and y squared we get here. So all this second degree term will go away. X square and y square will get cancelled. So we get line in this form. This line may represent the radical axis if the circles are not touching each other from the outside. It will represent the focal chord, not focal chord, the common chord actually, when the circles are intersecting each other, and it will represent tangent also when they touch each other. So we are assuming that they are touching each other. It means I'm assuming it is a tangent. So this line is the equation of a tangent. So how to prove it a tangent? It means that we have to just take the center of the bigger circle, and from there we drop the perpendicular. If the perpendicular length comes as the radius of the bigger circle, we are through. Or maybe any circle you can take, the center of any circle, but I'm saying it's easy because this is already origin. So when you drop a perpendicular from the bigger circle, from the origin, it should come A. So when it is coming as A, it means that this is common tangent. And when it's common tangent, it only happens when the circles are intersecting from inside, means one circle is touching the other circle from inside. So in this way you can also prove it. So I gave you two types of proof for this thing, and when we prove it, we can construct our own theorem, and that is actually I believe that's a correct way to teach the students. Alright, now we jump to the GeoGebra to see why it is actually true for any point on the circle, not circle, any point on the ellipse. Okay, so we are in GeoGebra now, and we are going to construct the whole scenario in animation form to understand deeply why if the point is moving on the ellipse, the circle we draw on the focal distance will touch the auxiliary circle from inside. So for that, what we have to do, I'm just taking any random ellipse to give you the exact feeling. So for that we are not taking any particular ellipse, we are taking random ellipse. For that I need to have this the denominators of x square and y square different, means it's changing, then only the ellipse will change. So for that we are constructing slider, and to construct slider we need two sliders. In fact, there is a A and B. So I'm taking A and we hit enter. That will give you the slider -5 to 5, which means that the value of A will change from -5 to 5. So of course I don't want the negative number, so for that I will go to this 3 dots and we hit the settings. In settings I have this slider, and in slider I want to change this minimum value of A to 0, and when I put 0 there, hit enter to confirm it's 0. We can increase the value of the maximum value of A. That is, it is 5 already, so I don't want to change it. So let's keep it as 5. Then for B I again hit the same thing. We type B and hit enter. When I hit enter, that is actually this -5 to 5 again. Again I don't want this negative, so I will go to the minimum value of this and change to 0 and hit enter again. So we have these two sliders which will act as A and B for the ellipse. Now I draw the ellipse. So it's not draw actually, it's just type in fact. And for that I have this x, first I type, then x squared. We go down to make it in the fraction, then hit forward slash to give the bar which divides the denominator and numerator, and then a square. Again I need plus, then y squared. Go down, again hit forward slash, that will become b square now, and after that I will type 1. So this gives you an ellipse. But notice the a and b both values are 1 and 1. That's why it is not looking like an ellipse, it is a circle. And you can see there's no axis there. So actually I disabled before that. In fact I disabled this axis, so let me make it appear. So here you have to just click anywhere in this canvas, right click, you get the show axis and just click it. It comes here. Now I want to see this is an ellipse, not the circle. So for that I am making this slider change. Okay, now I want to see this circle as an ellipse, so I will change the value of the slider. I will go to, let's say I'm going 1 point, 2 point, let's say 4. So I'm going to 4, and that will give you the length of major axis as 8, that is a 4, 0 and minus 4, 0, the two ends of the axis. And let us keep the value of b as 3, so I will increase it till 3, and that will give you an ellipse. You can also notice that when we draw the ellipse, I have the name of the ellipse as EQ1. This is the equation 1, and this is the name. It's important actually. We'll see it. Now we have to draw the auxiliary circle of the ellipse, and we know that auxiliary circle is the circle passing through the ends of the major axis. So center is origin and the radius is a. So we type x squared plus y squared is equal to a squared, and it will automatically give you the equation of in the picture of auxiliary circle, and this is giving you EQ2. So if you want to make the change of this symbol, this name also, we not actually feeling better, so we can also go there, we click here, and like this we click here, we get that, and we want to change it. So this is actually ellipse, so we call it as E, and hit enter. We hit enter, we get E as the ellipse, and now you see that the name is changed. And here is a circle, so I will call it auxiliary circle, so I will call it AC, and that's fine. This is AC. And now we have to draw the circle on the focal distance. For that I need a point on this ellipse. I also need the focus of the ellipse. So let's first find the focus of the ellipse. So it is not a big deal. We simply type focus. We type focus, we get the drop down menu here, and it's asking which conic you want to find the focus. So of course we are intended to find the focus of the ellipse. So we just hit enter here. We enable here, and after that we know that the name of the conic is E, so we input here E. As soon as we input, we got that the focus is somewhere here. Now the focus are named as A and B. I want to name it as F1 and F2, the generic name of the focus. So we simply go to this point A, and you can do the left click, and this will appear to the AA. That is actually giving you the idea that the name will be changed from here. So we say there, we hit it, and we get that thing to change. So that is F1 I want to make it. So let's say it's a F1. it doesn't matter which name you are giving to which. And again do the same procedure for B. So this is also changed. F1 and F2 are the foci of this ellipse now we have. Now I want a point on this ellipse. So which point you want to take? So actually the point should be not a fixed point, it should be anywhere. So that's only, then only we can understand the animation. So see here. So now I need So now we need a point on the ellipse, and this point should not be fixed anywhere, it should be a moving point. So it is not also a very difficult task. We simply type here point. So when we, oops, what is happening? P-O-I-N-T, point. And you can see there the many list. We have point on the very first place, that is point. And we go there, so this is recommending us point and object. So we hit it and we get the point object. It tells that it is asking that on which object you want a point. So the point I need on the ellipse, and you know the name of the ellipse is E, so we simply type it here, E, capital E. So we can see that the point is located somewhere here, A, and you can also see when you just press it and you can drag it anywhere. So of course I want to change the name of this point. Let's call it P. So again do the same process to change this point. Now it is P. You can see also when we have drawn a point here, we have a play button. This play button simply indicates when you play it, the point will travel on this ellipse circumference. So we can see that if you just play it, it's moving with some speed. Here there is a fast forward and all. This you can make the speed of, change the speed of this moving point. So let's keep it as a 1. And we pause it, it's point here. We can drag here. And now we are joining this P and F. So for that, I will take P, not P actually. I have to draw a segment. So for that I have to type segment. And that segment will give you the idea that I need point. So 2 points I need, the P and the F1. So P and, sorry, F2. And there's a F2. Sorry, F2. So we got a segment joined. And the length is F, indicating this is the F is the name of the segment actually. And now if you can see that I drag this P, this length is still changing without changing the position of the focus. And on that PF2 I have to draw a circle. PF2 I have to consider as diameter. To draw a circle in the GeoGebra there are many options, but usually I use this thing. Let me just show you. If you go to the circle, I have this point, radius number, circle, point, segment, point, and point. So I rarely use this point, segment, and point. I use only like which ones? Point, not semicircle, I need circle. So for that point and point. So in that, the first argument, the first point indicates the center of the circle, and the second point indicates the point on the circumference of the circle, any point on the circumference of the circle. So in this way, I need to find the midpoint of this PF2 so that I can say it's the center of the circle. And the P and F2, any of them I can take at the other point which is located at the circumference of the circle. And in this way we can draw it. So we have to find the midpoint. So there is a facility I have, the mid, to type the midpoint. So I will type mid, and we say the mid, this indicating that I have the option of midpoint. And we go to the midpoint, again this is in conic, a segment, conic, interval, and so on. But I need point because I have to find the midpoint of the 2 points. So I have the first point as P and the second point as, it's already F2. So we got the midpoint, and it is saying it's A. But in our explanation we called it M, so we call it M, let us say. And now I have the midpoint. Now the last step, we have to draw the circle on the focal distance. So for that I have already the midpoint, which is acting at the center of the circle, and I have any point on the circumference, so we can take it as P, either as P or as F2. So we call now circle. Let's call the circle. So circle, and here I am using this point. So the first point is always center, so I call it M, and the second point is any point on the circumference of the circle, so let's call it P. And you see what is happening is already touching the auxiliary circle from inside. So GeoGebra and all these mathematical tools are built in such a way that it will never give some wrong picture. Now you see that when we move the P, whether this circle is touching the auxiliary circle for any position of the P or not. And so for that, why not we can just play this button. So we play it, and you can see the circle grows, but still it is touching the auxiliary circle from inside. And that's the proof of the theorem visually. Alright, so that's all for today. We explored many things, I hope. See you in the next video. Stay math active.